and welcome to class number 2. We're going to continue with regression review, but we're going to get by the end of today's video to multi-level modeling, particularly a fixed effects model. And then we'll cover the basic idea of nesting, and this will set the stage for the rest of the class. I think most of the core content of the class is going to be discussed in its nascent form today. So at certain points, I'm going to be asking you to stop, take a break. I'm going to record all the way through, but I think it's important to pause and give yourself some cognitive energy to plow through some of the more challenging aspects of what we're going to talk today, because it really serves as a foundation for the rest of the class. So, busy slide, but simple concept. We have done, we want to understand something, and we're going to build knowledge by comparing groups. We start with a mean, and that's what this is, right? And then a variance, and that's what this is, right? So we've just got the mean of our y variable here, and then we've got the variance of said y variable here. You're familiar with all of these formulas, but the mean only tells us so much about it. The mean and the variance only tell us so much about any particular thing. And this is, importantly, this is called the marginal mean. The marginal and conditional will be something that becomes very important as we move into generalized linear models away from just the modeling of normal distribution based x's or epsilons, as the case may be. So this is not super important now, but it's going to become super important later. So this is the marginal mean, which is the overall mean. Like it's literally, when you look at a table, it's the mean at the margin. And we are going to condition this marginal mean on some x variable. In this case, we're going to use male. But what we're going to do is we're going to take this one mean and we're going to turn it into two means. We're going to turn it into one mean for male and one mean for female. And so now we just have two means, and that's all this conditioning means, that we are taking one mean, which is represented up here, and we're turning it into two means conditioned on what group you're in. So we're going to have a mean for men and a mean for women. And that's all we're doing. And in the case of a dichotomous variable, it's simple. It's totally the same as if we run it in a regression format, as if we run it in a t-test format. We'll get the exact same answers across the board, and we can decompose the mean in either situation. So this conditional mean with a dichotomous variable is a simple case. But we often have more than one dichotomous variable that we want to model, and so that's why we use regression, because regression allows us to add as many variables as we need in order to capture whatever data generating process we're hypothesizing about. And as such, we want to move to a system, and for most of the rest of the semester, we're going to be thinking of these mean comparisons, not in terms of actual means, but in terms of regression coefficients. And so regression allows us to make mean comparisons between different groups, levels, amounts, etc. So we're not just stuck with something that compares a continuous variable or an interval variable across a couple of groups. We can have multiple groups, we can have continuous variables, we can have a whole host of things, count variables, like the list goes on and on and on, and we can throw them all into the regression equation. But fundamentally, we're doing what we just did in that previous slide. We are just conditioning some y variable on a set of x variables and calculating the mean for various groups. So we're still doing that. That's all we're doing, and that's all we're going to do for the rest of the semester. All right. So we're going to use an example from the Multi-Level Modeling in Plain Language, Chapter 1, and they have this data set that runs through their whole book. So we're going to use that this time to think about how we're going to move from a system where we're just using regular old regression to where we're going to spend the majority of the semester looking at multi-level or nested data. And the Australian example includes a dependent variable that's a transformed reading score. So it's just a z-score reading score. The nice thing about z-scores is that we know it has a mean of 0 and a standard deviation of 1. And then we're going to use gender and parents SES to start with in order to understand it. So let's just run the basic model, right? We just have calculated a regression with male and uh, this is the parents. This is the status of the parent's occupation, the highest parent's occupation. Um, and so what we see here is regression. And if we try and interpret the coefficients, right? One thing we have for going for us is z-scores, our normal distributions. So mean 0 with a standard deviation of 1. So if we look at the constant, we know the constant is is a female, because male would be 1, so female is 0. So this is a 0 coefficient when it's a female. At this POS variable, which is I would just call it the SES variable, is at 0. But the SES variable has no zeros in it. So you can see that the minimum value is 16, the maximum value is 90, the mean is 52, and the standard deviation is 16. So this is a status that does not exist in our data. So this value is somewhat meaningless in the context of what we're doing. Well, I want to have this be a meaningful value for us, and I often want to look at what the constant is and understand it as the mean of some group that I'm using as my reference group across whatever thing I'm doing, and so I center my variables. And when doing this context, I want to center it at and there's. Last week we centered age at 20 because I wanted the youngest person in the sample. This week I'm going to center just on the mean. So we're just going to take the average parent's occupational status as a 0, and so it'll be the standard deviation will stay the same at approximately 16, but the min and the max and the mean will change. The mean will be fixed at 0, and then this will be negative to positive. So we center when we want to make these coefficients meaningful. That's one thing. Later in the semester, we're going to be using centering on the group mean to separate out the difference between the between and within variance. So centering has a lot of uses for us. Today we're doing the most typical and simple case where we just want to make our coefficients, particularly the intercept, the constant term, to be meaningful. So let me show you how. Oh, that's the wrong. Let me show you how I do this in a regression. Sorry, I forgot to clear all this stuff out for you. So here's my do file, which you have. So you have all of this. You can run it. You obviously have to change the path to the place on your computer where it is. This is where it's stored on. All the stuff is stored on my computer. You have to change that to your computer. But given that you do that, all of this should run perfectly smoothly. We're going to use data for chapter 1, which is the name of the data that comes with the book. You can download that, or I've uploaded it to the same place where the do file is. So we have that data in. It includes 4 variables: the Z reading score, male, which is just the gender dichotomous variable, the highest parent's occupation, and region. And we'll get to region in a second. Here we're going to just use this. We've already done this stuff. So to center it, all I do is create a variable called mean POS, and that mean is that variable is just the you can see here it is just the mean. It's the same all the way down, right? Turtles. So what that allows me to do is subtract this value, the parent's status, from this status. So this person has a high status. They're going to be a relatively high positive number. This person has a slightly negative status, so this person's going to be a little bit below 0. This person's going to be really below 0. This person's going to be above 0, right? So you get the idea. So nothing is going to change about the distributional properties. of our variable, but what will change is the coefficient for the intercept, and that's basically it. So here I just subtract them from one another and create a variable called CPOS, and that's the variable I'm going to use. And I'm going to do the same regression. Same regression is up here, except I'm now using the CPOS variable, and you can see the coefficient for male, if you look back on the slides, is exactly the same. The coefficient for CPOS is exactly the same as for POS. What differs is the constant. So now I can interpret this constant. This constant is the mean of a female whose parents have the average occupational status. So a meaningful number in the context of what we're looking for an average middle class female, we would expect her to have a reading score of 0.19. Because I know that z-scores have a mean 0 and a standard deviation 1, the typical girl, in this case they are girls, but females are about 1/5 of a standard deviation above the mean. Meaning that boys are essentially a 1/5 standard deviation below the mean. And each unit of occupational status increase, each increase in a parent's status increases by a rather small amount the reading score. But occupational status is a variable that has a lot of values, so we might want to think about this in terms of standard deviation units or something like that if we're going to spend some time interpreting. All right, so let's take a little bit more look at this formula and how we interpret all of the values. So if we want to predict the reading score for a female, we know the answer. It's 19 because this value is 0 for females, and this average, which I've said here, average SES parent, right, is going to be 0. So this is 0 and cancels out. This is 0 and cancels out. And so we know what the value for a typical female is. For a typical male, we just subtract this from this and get negative 19. So that's the average score for a male with an average SES parent. Now, I've been saying these are means, right? So we can use this regression. What I did here is I used the command, and this is the part of the thing that we've been talking about, right? Like I want you to use your models in the form of simulations, in the form of predictions, to understand what it is that you're doing. It's how we talk to our models and see how they're doing. So I created this variable called predict y hat. So predict just gives me the linear prediction for each person, right? So it just calculates this formula for each person. This formula for each person, right? So their values of male and their actual values, not fixed at 0. And then I just said, okay, give me the value of y hat if a male is 1, right? So I want males. And because I don't know how many people are going to be exactly at 0, I said, okay, give me let's just do the range from negative 0.75 to 0.25, which is clustered right around, and that gives me 320 observations. And here's the mean for that group. So I'm just taking males approximately at 0 and taking their y hat, their predicted value, and I get this mean. Whoop. I went a little too far there. So I get this mean, which is almost exactly the same as that parameter, right? So I can use the mean of this particular group, males with a parent at the average socioeconomic status, and just calculate the mean of all of their scores, their predicted scores, and get what the value is here. Now, if I took the mean of their actual scores, the variance would go up. So these folks have a very low standard deviation, but if I were to take the actual score, that standard deviation would go way up because of the stochastic process that we have here. My point is to say that all we do when we do these linear predictions is we're just getting the means of people at various points for various groups. And so what I want you to do is stop now and use the data, or you can do some math here. It's not that complicated. But what would you get if you were looking for the value, the reading score, the expected reading score for the typical male and typical female whose parents were at one standard deviation of the CPOS variable of the SES status? So take a second and see if you can get that, because we've covered all of the basics and you should be able to get it at that point. I will offer you one hint, and that's this number here. So we want one standard deviation score for males and females with parents at one standard deviation CPOS. Take a second. All right. I hope you hit pause, because I'm going to keep talking now, because I've already done it and I know what the answer is. You can, if you are struggling with it, you can take a look and see in the code, because I did the calculations in the code using status commands that allow us to extract the values for coefficients, which is always a very useful thing. Now, as I've said before, I find real value in pictures. And this is the picture of the model that we just had. So we can see along the x-axis the socioeconomic status of parents, right? So centered at 0, and it runs from a little bit above -40 to a little bit below 40 itself. And here's the reading scores. The typical male is represented by this blue line. The typical female is represented by this red line. And then you can see the spread above and below those lines, right? So the mean is right between those two lines. And so you can see that there's quite a bit of variability around that. It's not as if knowing a parent's socioeconomic status and a student's gender tells us exactly what their score is. It does so with a certain amount of error. And if you go back and you look at, I don't think I show it here, but if you look at in our model and you look at the root MSE and the R squared, you can see that there's quite a bit of variance left, and we've only predicted about 14% of the variance here. So there's a lot of leftover variance that we've not predicted, and you can see that in this figure, right? There's a lot of stuff we have not explained because there's a lot of variability around these lines that is not captured by the lines themselves or the slope. But the good news is that our model is at least looking like a reasonable approximation of the data. If you were to ask what is a typical value for male or female, these lines would not be bad representations as you move along the continuum of a parent's socioeconomic status. All right, so we have a sense that there's a relationship between economic status and reading scores and gender and reading scores, and we can see what it is with this picture. But you'll notice these lines are parallel between males and females. We've made the assumption, the explicit assumption, that it doesn't matter where you are along a parent's socioeconomic status. The difference between males and females is a fixed number. One number represents the difference between the female line and the male line, irrespective of parents' socioeconomic status. Now, one might imagine that parents with higher socioeconomic status have males that perform better than that the male slope is steeper than the female slope, in which case that would be an interaction, or it could be vice versa. The female slope could be steeper than the male slope. We just don't know. And so we want to test this question, and in order to test whether the slope for gender is the same across all socioeconomic statuses, whether it matters, it doesn't matter whether I know where somebody's parents are in terms of those socioeconomic status on the effect of gender, on the effect of on their reading scores. So does reading score by gender vary across socioeconomic status, right? Interactions are complex things to think about, but that's the question we want to know. And essentially, are these lines really parallel all the way across here? Or are they is there less distance up here and more distance down here, or some combination thereof? And that's what we test when we look at interactions. So we're going to test first for a male by POS interaction, and we do that in Stata by by the way, this is the code for that graph that I showed you. I always think it's important to look at the code for graphing because it's important to do, and there's a language of graphing. So in Stata, we do that by just including these two number signs here between the two variables. I've denoted this as a categorical variable and this as a continuous variable, and that's important for Stata because it gets angry if you don't do that. And so when I run that, I get the same thing that we see here. You don't need to see what I'm not getting from Amazon right now. And what we see here is that there's really not much evidence for an interaction between gender. If there is a difference between the slopes, it's really small. Now I want to highlight a command, a post estimation command in Stata that is incredibly important, a little bit complex to learn, but incredibly important. And so I think you want to practice with it as much as possible. I certainly still practice with it quite a bit, and it takes me a little bit of time to get the right thing, but it's the margins command. Contrast is another part of margins that is very useful, and we talked a little bit about that last week when we talked about different forms of indicator variables. But this margins command and contrast really help you understand what your models are and what your models are actually saying. So if we look at the interaction, what we see here with this margins command, what I'm asking for is I want the marginal slopes. I want the slopes for males and females, right? So I want those conditional slopes, and I want them assuming the change in parents' status, right? So I'm accounting for that status, and here we have the male slope is 0.19, the female slope is, the female slope is 0.19, the male slope is 0.20, so there's a little bit higher slope. But if we look at these confidence intervals, they totally overlap, right? Like the majority of these, or a huge chunk of these, are overlapping. So the variability in these slopes clearly accounts for the fact that would clearly explain these differences. So I'm not confident at all. In fact, I'm pretty unconfident that there is an interaction between male and female. And there might be a small one, and maybe I need more data, or maybe I need more better measures of reading scores. But given the evidence that I have, I do not feel comfortable saying that there's evidence of an interaction between male and female. And certainly, if you look at the traditional measure of the p-value, which I want to be cautious to not overinterpret, it would suggest that we reject this hypothesis that those are different. All right. I want you to take a break here because we're going to move into something a little bit more complicated. So hit pause on the video, go get yourself a cup of coffee, or whatever it is you're drinking at this time of day. Take a bathroom break, and then we're going to come back and we're going to start moving our regression analysis into the territory of multi-level modeling. All right, welcome back. So, the epsilon in the room. That's my attempt at humor. Usually I get feedback by people groaning or not laughing, but I have no idea whether my jokes are working. Nonetheless, we have this epsilon term from the regression that we had looked at before, and we've looked at each of these terms. We looked at the intercept, which is female. learned how this is a comparison, a direct mean comparison for males with a CPOS at 0. You, I hope, have figured out by now how to calculate the male and female values when the CPOS is at 1 standard deviation. The answer, of course, is that you just take this value would be 16 because that's a standard deviation, and multiply that out, and then do all of the simple math here. But what's left over is this stochastic term. And we've used this for various things. So last week we talked about the stochastic term in traditional regression terms. So we looked for heteroscedasticity, we looked for normality. Those are core assumptions. But we didn't really look at independence. And independence is this thing that we're actually worried about here when we talk about multi-level modeling, because we've assumed that each of the epsilons we have no more information about. It's just random noise. We have no more information about the relationship between two epsilons. Each one is its own little thing. They're not related in any way. Other than just through some random process. And we almost never mean random. What we mean is like there's lots of little processes going on, and those accumulative little processes, and this is the the magic of statistics, that all of those multiple little processes add together to create what looks like random noise. And there's no systematic relationship between two students that exists in this data other than is captured by the model that we have. And that's what independence is. But we have a grouping. So I told you this is Australia, and this is a map of Australia. And Australia is a very large country. It's about the size of the continental United States. Western Australia, there's nothing here except a really beautiful city, Perth, right here, and some other beautiful coastlines. But this, all of this stuff is empty. There's nothing there. I don't mean to disparage the people in Western Australia. There's I'm sure lovely things out here, but it's not well populated, is what I mean by nothing. There's Darwin up here, and then not much in here. There's not much in South Australia. Queensland is pretty empty. New South Wales is where most people live, and Sydney's right here. Melbourne, the other big city in Australia, is right here. And then there's the ACT, which is just the capital, and it's like Washington, D.C. here. Tasmania is over here. So we have these different places, and in some of these places, like the Australian capital, everybody is like Washington, D.C. You have a high concentration of professionals and lawyers and people like that, so you'd expect those people to have different educational statuses than somebody whose parents are coal miners, even people that have a relatively high status as a coal miner who live out in wide open territory, or sheep farmers in the Northern Territory, or whatever. You would expect that maybe these geographic units explain some of the variability in reading scores. And that would be a violation of independence, because students in New South Wales are more like students in New South Wales than they are like students in Western Australia, violating our assumption of independence. That suggests that there is something other than random noise explaining the remainder of student scores, right? The variance we've explained a little bit with parents' socioeconomic status. We've explained a little bit with gender. In fact, our models tell us we've explained about 14% of it with those two variables. But after we explain those two, that 14%, the stuff that's left over, some of that might be explained by territory. And if that is the case, then New South Wales students are more like New South Wales students and are not independent of each other. South Australia students are more like South Australia students than they are like Queensland students or Northern Territory students or Western Australia students, and that is a violation of independence. And so that's what we're going to model as we move to our multi-level modeling framework. That's what we want to capture. We want to understand these similarities between our observations, in this context students, that aren't accounted for by the other parts of the model. And we're going to use a variety of techniques in order to model that. So one thing we can do is get the residuals. So in Stata, I'm going to rerun the model here. And then I'm going to use predict, which we've seen before, right? That was the predict y hat. But if I put comma res after it, then I get the residuals. And so now I'm going to predict the residuals. And so now I have a variable called residual. You can look at it. There's nothing mysterious about it. And it represents, mechanically, the difference between my predicted value reading score. So this person has a much higher reading score than is predicted. In fact, a much higher reading score than predicted. So this is their reading score. This is their predicted reading score. And we have this chunk left over, right? So this is what our model says they should be, but this plus this is what they actually are. So this minus this is how we get the residual, right? So the residual is the predicted value minus the observed value. And this tells us a whole bunch of things. One thing we're going to look at right now is what is the relationship between the remaining variance as captured by our residuals and region. And I've just run an ANOVA here. So I just took the residuals as the dependent variable. So I'm predicting the residual, the remaining variance in reading score, not accounted for by male or by parent socioeconomic status. And when I do this, I see that I predict very little of the variance, about 3% of the variance is accounted for by the model, which in this case is region. But there's reason to believe that region is not zero. It's not trivial. It's not a trivial amount of variance. It's an amount of variance that is different. It stands out from the noise. So we have a problem. We have a violation of our assumption of independence. And good news is we know what it is. We've identified the source of that violation, and that's knowing something about somebody's region. So now we can begin to model that. Sorry, that's the wrong thing. Okay, so let's start by looking at region and z-scores and begin to explore the effect of region on a student's score. So the first is that tiny little area, ACT, the Australian, where the capital is, and that's just that's the little city of Canterbury. Is it Canterbury? I think so. Anyways, I'm not an Australian geographer. I don't know much about Australia, but we can see the mean values, and we can see that there are differences across these mean values. There's a lot of variation, but nonetheless, we have reason to believe that that the scores of students would not be the same in each of these places. This picture is the same as this graph. Personally, I prefer the picture. I think the picture tells me a lot more than the graph. And what the picture tells me is that Victoria, where Melbourne is, has the lowest scores. And so the rest of these guys look pretty similar, but Victoria is where the real action is in terms of low scores. So it looks very different from the others. But there's a sense that there is some movement here, that these scores are not, you can see the confidence bands here. These scores are not overlapping. So now I want to explore a little bit more in detail about the scores. So we can just look to see that there's, we've got about 1,300 students. I'm just looking at the distribution. So there's enough people in all of these areas that I can begin to explore that. What we're gonna do in the first step, right, is we're gonna run a regression for each of these, and that's why I need to look at this to make sure that I have enough sample size in each of these regions to run a regression for ACT, and a regression for New South Wales, and a regression for Victoria, and a regression for Queensland. So you can do that in Stata. Of course, you can do that in Stata. So we've done all of this. This is the margins plot for region. So again, that's how I got the margins plot, that plot that you see here. This one right here, I got through margins. It's called margins plot. So margins is really, really useful. I don't know if I've said that before to you. I actually do know that I've said that to you before. So here we have the different variables or different regressions. So we're going to regress for the first region, the second region, the third region, the fourth region, the fifth region, the sixth region, the seventh region, the eighth region. We're just getting a regression for each region. There's nothing magical about what we're doing here. We're just running a separate regression for each geographic unit. And that allows us to get a slope for each geographic region. It allows us for male. It allows us to get a slope for socioeconomic status. It allows us to get an intercept. And by doing so, we're able to get an accurate assessment of within each region what's the effect of each of these variables. And the benefit here is couple-fold, right? One, we get each of the independent slopes, and we can see here that the slope for male and I think this is the ACT region, is, actually I don't know that that's the answer. I don't know what these regions stand for, so I'm a little bit lost here in terms of that. But we can see that the slope for 3601 is less steep than the slope for 3602. Which is about the same as 3603 and 3604 and 3605. These are very similar male slopes here. So I'm just looking at these values. That one's a little on the low side. That one's really on the low side. So that's a really low slope. So there does look like and if you look at the confidence bands around them, there's reason to believe that we might have different relationships between gender and reading scores as you move across these regions. So not only are there differences in the intercepts between these regions or the means between these regions, but there's differences in the relationship between gender and reading scores in each of these regions. And you can imagine a whole host of reasons why. If we look at this variable of socioeconomic status, here the slope is relatively steep. Here it's about the same, but a little less steep. Here it's about the same. So those seem pretty similar. Here's a little less steep one. Here's a little more steep one. Again, a little less steep one. So there is a little bit of variability around that. So we might have evidence of a different slope. So we have a tool for testing that kind of relationship, right? And it's so the first thing we do is we're going to look at the different intercepts, and we're going to see is there evidence for differences across the intercepts. And all I've done here is created a variable called, I've used the variable called region. I put the I dot region in front of it, and it gives me a coefficient for each region. So now what this model is this model allows for each region to have its own intercept. So this constant right here, I'm going too far ahead. This constant value right here, I'm sorry, let me just stop and show you the regression here. So it's this right here. So I'm just taking the reading score. I'm using region as an indicator, like you would use any other indicator, male and CPOS. So the slope for male is going to be the same across all regions, and the slope for CPO for socioeconomic status is going to be the same because I have not created any interaction terms. So the slopes are consistent across the regions, but the regions each get their own intercept. And that's what this allows for. And we can go back and we can interpret this. So the intercept for the ACT region, which is the baseline character, which is the default, is minus 0.68. For a female, I'm sorry, whose parents have 0. Let me actually do that right here. Okay, I'm going to use this one. I'm sorry, I did not update my slides. So here we go. So a female with a parent at the centered socioeconomic status, and I know it's female because that's 0, all of these are 0 for ACT, for the ACT region, right? Because these are all indicator variables. So ACT is the default variable. So this constant represents the typical score of a female whose parents have the average socioeconomic status job, and that's this person's reading score. If I want to calculate for that same type of female, a female with an average parent score, but in New South Wales, I need to subtract 0.075 from this constant value. And so this is how I can reconstruct different means for different females or different males with different levels of economic status, parents with different levels of jobs. For each of those groups, I can use this data to calculate the means of those. But so this indicator approach, we're going to, at some point, we're going to call this is going to be one of our fixed effects estimators, which works well in this context. We're going to use other fixed effects estimators for different ones, because you can imagine that for each group, having a separate coefficient can get overwhelming sometimes, because sometimes we have lots of groups, right? So if you're looking at kids and you're following kids over a couple of time points, and you have 1,000 kids, well, that would be 1,000 parameters. Here we only have 7 geographic units, and so it's not that hard to create seven different intercepts. But that's all we've done here. So now each region is allowed to have its own intercept. But we noticed from these regressions up here that we ran that we might have evidence for different slopes for the effect of male and for the effect of socioeconomic status. And in order to get different slopes, what we need to do is run a regression with an interaction term. And so we can do that. We can regress reading on an interaction between male and region and an interaction between CPOS and region. And so we're just going to create 2 different interactions. We're going to allow each of these slopes to vary across region. So we have a different, sorry, let me put the I in there so Stata doesn't get angry with me. So we're going to have different intercepts for each of these, because when you do this double number sign, it creates the interaction term, but it also includes male and region and CPOS and region in addition to the interaction term. So it does it the right way. And so when we run this model, we get a rather large table that has our male coefficient. And so this would be, so if we wanted to know what the value is for a male in the ACT region, we have this value and this value, right? But if we look through, all of these would be 0 because they're an ACT region. All of these are 0 because they are an ACT region. The parent is at the average socioeconomic status, so that's 0. And then all of these are 0 because the region is ACT, and it's 0 for that. So in order to calculate a male in the ACT region, all we do is we take this number and we subtract it from this number, and that is approximately 0, right? So that person is right at the mean. A male in the ACT region has a score of 0. This is the slope for the CPOS variable for that person. Here's the slope for male for that person. So this is the ACT slope for male. This is the ACT slope for socioeconomic status. If we wanted to get any of these others, we need to use our linear equation here and add them together. Now, that's one way of doing it, going through and mechanically adding all of these all together. So for example, for New South Wales, for a male in New South Wales, I take this value and the New South Wales intercept here, and the New South Wales, and then the male slope goes down a little bit more. So New South Wales for male, the slope gets this number added to this number. And then for CPOS, the New South Wales number here gets added to this number, and then we add that all to the constant, and that's how we get the term. There's a lot of stuff going on there. I strongly recommend that you at least work through a couple of them to see how it works mathematically. But I would not recommend ever doing that because A, your math can be wrong, but B, you also don't get standard errors and other things that you want to see. So this is where we use our friend margins. I'm just storing the estimates here because margins wants the stored estimates, and it's easier to do that than rerun the regression. And that's a tool that we'll use a lot. So when I run regression, I just store these estimates so I can call them back. But here I'm running the margins command, and I'm saying I want to see the marginal means for this region by male interaction. And when I run that, what I get is all of the values for, so this is the slope for a female, or this is the mean for a female in the ACT region. This is the mean, and remember when we calculated the mean, it was really functionally 0 for a male in the ACT region. This is the mean for a female in New South Wales. This is the mean for a male in New South Wales. And wow, look, see, you notice that this difference is a little bit narrower than this difference. So females do a lot better in New South Wales, and females do a little better in New South Wales. Males do a lot worse in New South Wales compared to the folks in the ACT region. Victoria, both of the males and females do much worse. And whew, look at that male score. So those males are not doing well there at all. And so you can see what the scores are for each of them. And so margins is really helpful in that regard. The other thing is we can look at a plot, and we just ran the margins plot command. So here's the plot of those means. And I find that personally for interactions, the plots almost always tell me more. So you can see where they're closer. So the blue line is for female. The red line is for male. The green line is the average between them. But you can see they're more tightly clustered. The difference between male and female is smaller in the ACT region, is larger in the Victoria region. I'm just looking at the distance between these things, right? So Queensland, it's relative, there's some pretty large differences, but the new territories, it's relatively small. It's a smaller distance. So you can see the interaction by looking at the differences between these. So remember, in the previous model where we assumed that all of these, that the slopes between men and women were parallel to one another, here we can see that there's some differences between males and females in terms of this difference, and some of that difference is explained by the region. The regions have different levels of distance between male and female scores. All right, so we've explored the male by region interaction, and now we can explore the effect of socioeconomic status on a parent's on a child's reading score. And so I'm just going to restore those estimates. And then rerun the margins command, but I'm going to look at region, and then because CPOS is a continuous variable, I'm going to tell it where I want to look at the means for. And so I say, okay, so it runs from negative 36 to positive 36, but I did 35 to positive 35, so that's the range. And then I want you to tell me every 14, and by 14, I just needed to chunk up that distance in equal units. So those are equal units. So I can run that. All right. So here we have, and we can see, right? So CPOS at 1 is negative 35. 6 is 35. So we've got the scores, the value of CPOS at negative 35, which would be a very low socioeconomic status job for a parent. Negative 21, which is also a low status, sort of middle of the road, a little bit below the average status, then a little bit above the average status, and then way above the average status, and then sort of the top status people at our number 6. And then you can go through and you can see, here's what the different means for the lowest status people are, and you get confidence intervals and standard errors and all of that stuff, so you can see how precise our estimates are. You can see that in Victoria, the lowest status people really do really poorly. So a lot of the action is in Victoria again. You can see that there's for people like in ACT, there's a pretty strong drop off in the effect of socioeconomic status. It pretty quickly stops mattering to these folks. These folks jump to zero pretty quickly. But there's some evidence of difference in slopes here. We see that when we look at there's some evidence that there are differences, and now this would be the difference between each of these values and the ACT slope, right? Because the ACT slope is our baseline. So, but there's some evidence for interaction effects. And again, not to overvalue p-values, but just a quick reference, they tell us that. So this is a hard table for me to look at. I don't know about you guys, but it's going to take me it would take me quite a while to parse through this. I like pictures, as I've mentioned before, so I just run my margins plot, and because I've set everything else up nicely, here I get these are the slopes for each of these regions on the effect of parent socioeconomic status on reading. And so some of these slopes are more steep than other slopes. So if you look at this dark blue slope here, the dark blue slope is our ACT slope, and it's pretty steep. There's a pretty strong gradient between socioeconomic status and reading scores in kids, where some of these other slopes are less steep, right? So the New Territory slope is less steep. The Tasmanian slope is less steep. So some of these slopes are more steep, which means the effect of parent socioeconomic status is stronger on reading scores, which is not a good thing, right? Like that's more of that's evidence of inequalities, whereas less steep slopes is evidence of less effective inequality on reading scores. So knowing something about these slopes tells me something important. There's evidence, and you can see it in the picture, that these slopes are not all the same. These lines are not parallel. If these lines were parallel, there would be no interaction, but these lines aren't parallel. So what we've done at this point is we have run models that allow us to look at, and I just put the plots here. So this is the male plot, this is the CPOS plot. So what we've done is we've allowed each of the regions to have their own intercept. We've allowed each of the regions to have their own male slope, and we've allowed each of the regions to have their own slope for socioeconomic status. So now we've done the same thing that we did when we ran those separate regressions. When we ran a regression for each region, we got its own intercept, its own male slope, and its own CPOS slope. With the interaction, what we've done is we've allowed in one model to have every region have its own intercept, its own male slope, and its own CPOS slope. So all we've done here is redo what we did when we ran the separate regressions for each one. So all of this is exactly the same as this, with the exception that here we get confidence intervals and p-values, and we can make comparisons and use our statistical tools. But these are the exact same process, and give us basically the same information. If you went back and you looked at what these are, you would find them to be very similar. Now here's a super difficult question. There is one difference. There's a couple differences, but there's one difference that I'm thinking of between these two different models, and I'm wondering if you can figure out what it is. What are we doing here in this one model that we don't get in these separate models? Think about it for a second. All right. I'll tell you when we talk in class. So why don't you take another break? That was a pretty heavy chunk of stuff, and we're going to end with nesting. All right, welcome back. Now, we've just explored nesting. We were looking at students nested in geographic regions. In the context of Australia, it was the 7 Australian territories. So we're obviously not going to be spending our careers exploring Australian territories' educational outcomes. So we're going to want to think of nesting in a much broader term. So in a technical definition, nesting is data clustered in exchangeable units. And by exchangeable units, I mean that you can substitute one unit out for another unit that have some shared variance that violates the assumption of independence between observations. So classic examples are children nested in families. So you've got mom here, and you've got 2 kids. You've got or maybe you have, I guess that's not mom's name. That's a family name, and you've got 2 kids, and you have a family and 2 kids, and you have a family and 2 kids, right? And in some sense, families share a whole bunch of stuff. So they certainly share socioeconomic status, but they also share genetics. They might share a host of other attributes like how much drinking is going on, or how positive are parents, or what's parents' education status? What kind of value do they place on education? Right? Like we just can go on and on and on about the ways in which Sam and Pat are going to be more closely aligned than Sam is with Jim, and Jim is going to be more closely aligned with Tom than Tom is with Mel. Because as you move from one family unit to the other, you're jumping over a much larger difference than you are as you jump from within family. So the within variance is going to be different than the between variance. We can separate out the between variance between family units and the within variance between units within that family. And that's what we did when we talked about the ANOVA. And that's what we're going to be doing. We're going to be separating the differences between the Joneses and the Patels from the difference between Tom and Jim and Rod and Mel. So one way is to think about this cross-sectionally. The other major way we do this is longitudinally. So we might observe Eric at time 2 and 3, and Eric at time 2 is going to be more similar to Eric at time 3 than Eric at time 3 is to Susan at time 1. For obvious reasons, because Eric is Eric. And Eric has Eric's attributes. And Eric has Eric's height and his hair color and his disposition and his intelligence and his blah, 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 blah. Right? So Eric has more in common with Eric than Eric does with Susan. And so Eric at time 2 and time 3 is going to be more highly correlated than Eric is at time 3 with Susan at time 1. And that stronger correlation within Eric than between Eric and Susan violates this exchangeability. It violates the assumption of independence. They're not, whether you're at Eric at time 2 or Susan at time 1, you can't just plop them in as we've assumed we've drawn from the same population, because we haven't. Eric is Eric, and Eric's Ericness is getting in the way of me comparing Eric at time 2 with Susan at time 1. Same with Susan. Susanness is capturing more of the variability. I know something if I know that this is Susan at time 1, and it's not perfectly exchangeable with Eric at time 3. And by exchangeable, I just mean that they're random draws from the same population. So there's lots of different kinds of things that we can do in terms of nesting. We have siblings, we have geographic units, so we've explored the geographic units in the previous one. We can nest in most nouns, persons, plants, dogs, time. So there's lots of things we can nest in. We can nest across raters, so we'll use it for measurement. This is a tool that we can use for measurement. We can nest studies. That's what we do in meta-analysis. In fact, the random effects meta-analysis is the way to go. The fixed effects has a whole bunch of, unless you have very specific assumptions met, the fixed effects meta-analysis really has some problems. I use nested models with IRT or SEM. These are measurement tools. That's what you do. You're just nesting items in a person score. So items are nested in persons. So we use nesting data in a lot of ways. These are very, very useful tools to think about. It extends beyond just looking at families or geographic units or people over time. Um, so so we're going to be looking at a lot of these, and we're going to start with some measurement stuff for a clear example next week, and then we're going to move on and we're going to talk about these. Now there are some there's this two basic type thing that I mentioned before. So cross sectional, where we look at a single point in time across units that share something. And longitudinal, where we look across time, so we can look, so for example, a person at time 1, time 2, a county at different times, et cetera, et cetera. You can stack these. So you can look, for example, at classrooms with students nested in them, and then look at the students over time. So we observe students at multiple time points. So you can stack the cross-sectional and longitudinal nesting structures, and we can build more complicated nesting structures. Once you understand the basic nesting structure, adding it's sort of trivial. Like a 3-level model is not that much more complicated than a 2-level model. You're just adding another level. But the idea here is that what we're doing is taking shared variance and splitting it up to a between group variance and a within group variance. And this between variance is going to be something that we model, and the within variance is something that we model. Now, this within is going to still be called epsilon. So these are our epsilons, but we're going to be adding a new variance that we're going to explore, and there'll be that we might add multiple new variances, but initially we're going to start by just looking at the differences between the groups. We already did that. That's the model where we allowed each of the Australian territories to have its own intercept. That was how we compared the between variability for Australian geographic units, Australian territories, right? We knew something about the intercepts for ACT versus New South Wales. That is how we modeled the between variability between different geographic regions in Australia. We still had variability within students within those regions. Not all students in ACT were the same, right? So there's still that variability, and that's the within ACT student variability. So we have the between geographic units variability, between the Australian territories variability, and then within each territory, we had the within variability. So students still varied. And we were able to model some of those differences, right? We were able to model differences in how socioeconomic status or gender varied within each of those geographic units. So we had a within model and we had a between model. And so we've already done all of it. You can just stop right now. You're done. That's a joke, of course. So that's what we're going to be spending the semester doing. That's the basic idea of nesting. We're going to explore nesting. We'll be more concrete about what random and fixed effects are. We'll be more concrete about what these variance terms are, and we'll get fancy Greek letters to represent them. But we're gonna end today's discussion with a brief discussion of why we do this, why we use these kind of models, and these models have a lot of tools. A lot of value for us in terms of understanding the world. So one problem that we often have is the ecological fallacy, where we generalize group characteristics to individuals. And we did that. Remember, if you think about what we were doing, we were saying that these geographic units have certain attributes, and we were saying that students in Victoria or ACT had higher scores than students in Victoria. But that doesn't tell us much about any individual student. There wasn't much variability explained. And so we often will confuse, oh, you're a student from Victoria, you must not be a good student. That's actually not an accurate statement, because we don't know that much about. We don't know that knowing your geographic unit doesn't tell us that much. But we often make this ecological fallacy of generalizing group characteristics to individuals. And they're different processes. Vice versa as well, generalizing from individuals to groups is the atomistic fallacy. Now, both of those fallacies exist when you're looking at data where individuals, where smaller units are nested in larger units, and it just depends on whether you're looking at the group characteristics or the individual characteristics and trying to transfer those to then move them across those levels of nested and nester and nestee. But by combining them, we can ask questions across them, and we can isolate effects within each of the groups. So we can know how much is at the group level, how much is at the individual level, and then we can ask questions about that. We can run interactions between those levels. We can look at those effects, and by combining them, we really allow ourselves to understand the interactions and the characteristics and to isolate the effects at various levels. So this gives us a much more sophisticated tool for understanding the effect of groups and the effect of individual attributes on some outcome that we care about. And that's what we're going to be spending the rest of the semester talking about.